Hello everybody. So today we are going to talk about matrices associated with graphs. And let us start with an example. Here is a graph. We have our vertex set here consists of 6 vertices, and we just enumerate them 1, 2, 3, 4, 5, and 6. Now, and there are some edges, as we can see. So basically this matrix A, so which is called adjacency matrix, it's just going to record which vertices are connected and which are not connected. So the matrix is going to be 6 by 6 by the number of vertices, and the columns and rows both are going to correspond to the vertices. So let us enumerate the rows. So we have 1, 2, 3, 4, 5, 6 rows corresponding to the vertices 1, 2, 3, 4, 5, 6, and same thing for the columns. Now on the diagonal we simply put zeros. So the diagonal elements, diagonal entries of the matrix are going to be just zeros. And then off the diagonal we just put 1 if the corresponding vertices are connected by an edge, and 0 otherwise. So say 1 and 2 are connected, so we put 1 there, and now that this is going to be symmetric. So 1 is connected to 2, 2 is connected to 1, so this is this edge. So we put 1 there. 2, then 1 is also connected to 3, so we connect those as well. We put 1s there as well. 1 is not connected to 4, so we put a 0 there. It is also not connected to 5, so put 0 there. And it is connected to 6, so 1 there. So we have this third edge connecting 1 to 6. And and we continue in the same manner. So 2 is connected to 3 over here. So we put 1 here and 1 here by symmetry. 2 is then 2 is not connected to 4, right? So with zeros there. 2 is connected to 5. So it is this edge over here. So 1 and 1 there, and it is not connected to 6. Then 3 is connected to 4. 3 is connected to 5. And 3 is also connected to 6. This is this edge over here. Okay, now 4 is connected to 5, but not connected to 6. So zeros there. And 6 and 5 are also connected. So that is our matrix. Now, so this is the adjacency matrix, and it corresponds to this graph. One thing I want to show you here, to note here is that the matrix it does depend on the order of the vertices. For example, if I change the order, say this 5 and 6, let us switch them, and that this be 5 and this be 6 now, right? So here are the columns now. Let me put them in green. 5, 6, 5, 6. The matrix is going to be slightly different. So in fact, the first 4 rows and the first 4 by 4 portion of it is going to be just the same, right? So this kind of portion is going to be just the same because those are the same vertices. So we got 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0. But now what happened with the other two, the last 2 columns and last 2 rows, is that they switched. So basically So what does it mean? That means that columns 5 and 6 switched. So we got 1, 0, 1, 0 here and 0, 1, 1, 1. Right, that's how these columns, these vertices 5 and 6 are connected to the first four vertices. So we just need to switch them because the vertices got switched. And here by symmetry, same thing. And then the last 4 entries. So what's gonna happen? So on diagonal we still get zeros. Well, yeah, and 5 and 6 are still connected. So basically nothing happens there in this quadrant as well. So the only portions that changed actually are these two. All right, very good. So those are matrices. So one thing I want to also say is that sometimes we will use these notations. So we have this matrix A, so for the entries of the matrix, we will use this notation. We put A in the square brackets like that, and then we just put some indices. So let's say indices 3, 4. So what does it mean? That means that we take third row and fourth column, and so in the intersection we get this 1 there. So maybe let me indicate this by color. So this 1 corresponds to this one. So this entry is A34. So this is adjacency matrix, and here is a more formal definition. So we did an example. Let's do a definition. So let's say we have a graph with vertex set V and edge set E, and it is of order n, and moreover we know the vertex set. That will be V1 through Vn. So sometimes we just have 1, 2, 3, 4, 5, 6, right? Sometimes we prefer to say that the V1, V2, V3, both ways are fine. So then we get the n by n adjacency matrix with the entries A11, A1 through, so we have A1, 2 here and so on up to A1n. So you see that the first index corresponds to the row, number of the row, and the second index corresponds to the number of the second index corresponds to number of the column. So we got this matrix, and the condition is that Aij is equal to 1 if I and j are adjacent, Vi and Vj are adjacent, and 0 otherwise. And according to our notation, so we can also this entry we also denote a n square brackets with the indices ij. So that's just another notation for it. Okay, so that's the matrix. So far so good. So turns out that an interesting thing you can do with the adjacency matrix is to square it and see what happens. So here is an example. So our first example is kind of too large. I don't want to compute the square of a 6 by 6 matrix. So let's do a smaller example. So here we have a graph with 4 vertices. So here is the adjacency matrix. So we got zeros on the diagonal, as always. Now V1 is connected to V2 and V3, but not to V4. So the same thing in the column. V2 and V3 are connected, but V2 is also connected to V4. And V4 and V3 are not connected. So this is our graph. Now let's try to compute. Let's compute the square of this matrix. This is our matrix. I'm sorry. Let's compute the square of our matrix now. So here is our matrix, and we are going to multiply it by itself. So here it is. So okay. So how do we multiply matrices? Well, I hope that you had some linear algebra experience, but if not, and even if yes, I will remind you. So here is how we multiply matrices. We look at the first matrix, we look at the first row of the first matrix. So this to get the first entry in the first row, we take in the product we take the first row of the first matrix and the first column of the second matrix, and we multiply them one by one. So we got 0 times 0 plus 1 times 1 plus 1 times 1 plus 0 times 0. Right, so we multiply the first entry by the first entry, second by second, third by third, and so on. So in total we get 2 here. So that's 2. Now to get the next entry in the same row, we take the second column here. And we do the same thing. I don't want to write it anymore. So we'll get 0 times 1, 1 times 0, 1 times 1, 0 times 1. So that's a 1. Now the third column, to get the third element there, we need the third column. So we got 0 by 1, 1 by 1, and then 0. So it's again 1. And the last column here also gives us 1 in the product. Now for the second row, we take the second row and we repeat the procedure. So that is going to be 1. Then multiplied by the second column, we get 3. By the third column, we will get 1. And by the last column, it's going to be 0. Okay, let's look at the third row here. So we got a 1. And in the second column, it's a 1 again, then a 2, and then again a 1. And finally, the fourth row, we multiply the fourth row by all the columns. Note that as we do so, this fourth row is kind of simple. There is only 1, 1 there. So basically what it's gonna do is gonna pick this row out of the second matrix. So it's going to be 1, 0, 1, 1 here. Right, because all other entries are going to be multiplied by zeros, and these are going to be multiplied by 1 each time. So that's the product. That's how we multiply matrices. Now this matrix A squared has some interesting properties. So it turns out that the entries of this matrix have some important meaning in terms of the graph. So first, let's look at the diagonal values here. So this is 2, 3, 2, 1. So those values are exactly the degrees of our graph, right? So the first vertex has degree 2, second vertex has degree 3, third vertex has degree 2, and fourth vertex has degree 1. 2, 3, 2, 1. So those are exactly the elements on the diagonal. So yeah, let me write that. So diagonal entries are the degrees of the vertices and so that's diagonal entries. And it turns out that non-diagonal entries, say, let's take maybe, okay, so which color? Okay, let's be green. So say this entry. So what is this? This is in the first row and third column. So we have the first vertex and we have the third. So it turns out that this one counts number of walks of length 2 from V1 to V3. So indeed, there is one path like this, one walk like this. We can go like this, and that's the only way to get from V1 to V3 in exactly 2 steps. So let's maybe try one more time. Say this 0 is in the 4th column and the fourth row and second column. So we're talking about V2 and V4, and we can see that there are no walks of length 2 from V2 to V4. So connecting these two vertices. That's why we get 0 there. So it's again, the 0 is the number of walks of length exactly 2 between the corresponding vertices. Furthermore, if you think about, so yeah, let me maybe write it. So if you take a squared I j, that is going to be the number of walks of length 2 from Vi to Vj. I also want to notice that our statement about the diagonal entries in the matrix also fit well into this picture. So, for example, if you if you let me maybe add a page here. So, for example, so here is our graph. Let me draw the graph one more time, right? So our graph, something like this. And we have vertices V1, V2, V3, V4. So if we look, for example, at the vertex, say V3, and let's say, so how do we, what are the walks? Consider and let's count the walks. I'm sorry. It's yeah. So we look at V3 and let's think about the walks of length 2 from V3 to itself. So how can we do it in 2 steps? Well, the only way we can do it in 2 steps is to take some edge, walk along one of the edges, and then immediately walk back along the same edge. So we'll get V3, V1, V3 in this example. And we can do it with respect to any edge at V3. So we can also go from to V2 and then immediately come back. So that is V3, V2, V3. So the number of such walks is exactly the degree of our vertex. So the number of such walks is equal to the degree of our vertex V3, because we can do it for every edge at V3. So that's why on the diagonal we get the degrees. All right, so that's an example, but let's now prove this. Prove it as a theorem. So here is our theorem. here is our theorem. So let's say we have a graph, and the vertex set is v1 through vn, and A is our adjacency matrix. Then for any positive integer k, we can consider the matrix A to the k. So we multiply A by A k times. Then for any indices ij, the entry of our matrix A to the k ij is then equal to the number of walks of length k from vi to vj. So now for the higher powers, we are going to count walks of higher length, right? So for the square, it was walks of length 2. For cube, it's going to be walks of length 3, and so on. So that's our theorem. Proof. The proof is going to be induction in power, induction in k. So the base case is k equal to 1. So walks of length 1 are just edges, right? And so we exactly get the adjacency matrix. So if the two vertices are connected by an edge, then there is a walk of length 1 between them. If not, there is no walk of length 1 between them. So that's adjacency matrix. So that's the base case, k equal to 1. Now we have the induction step, right? So we need to do induction. So we assume that for some fixed k, we already proved this statement. We proved that the entries of the kth power of the adjacency matrix count walks of length k between the vertices. Now we want to count the walks of length k plus 1 between some two vertices, vi and vj. So we want walks of length k plus 1, but we already counted walks of length k. So we need to reduce walks of length k plus 1 to the walks of length k. How are we going to do that? Well, if we want to get from vi to vj in k plus 1, exactly k plus 1 steps, then we have to get to one of the neighbors of vj in k steps. So we consider all the neighbors of vj, and then we need to get to one of them in exactly k steps. So k steps. And this will give us all the possible walks of length k plus 1 to vj. So we need to get in k steps to one of the neighbors of vj. That's the idea. So let's write down some formulas. So we want to compute the number of walks of length k plus 1 from vi to vj. So from this idea I just described, this is the same as the sum over all the vertices that are neighbors of vj, so all vl, such that vj is an edge, right? And then we need to sum up the numbers of walks from vi to vl of length k. But now this number here is, we know it. By inductive assumption, this is the entry of the kth power of A. And IL, right? So the walks are from VI to VL, so this is ILth entry of the kth power of A. So we can rewrite this as this. So the same summation over all the neighbors of Vj, but now instead of this writing in words, number of walks from Vi to VL, I am just writing the entry, the corresponding entry of the kth power of A. Now now the thing is that we are summing up over some of the vertices, so specifically over all the neighbors of Vj. But what I can do here, I can kind of add this extra term here. So here we are summing up over all vertices that are not neighbors of Vj. So we are not Vj now is not an h. But I'm multiplying by 0, so this whole entry is in fact 0. So I'm not really adding anything. So I'm just doing it for convenience. And you'll see why this is convenient. So the point is that we have 0, we're multiplying by 0, and here we're multiplying by 1. But we can think of this 0 and 1 as the entries of the adjacency matrix, right? So in this sum, VL and Vj are connected. So this is the entry. So the corresponding entry of the adjacency matrix, the Lj entry, is 1. And here they are not connected. So the corresponding entry of the adjacency matrix is 0. So we're just multiplying by this entry of the adjacency matrix. So altogether, we can shortly rewrite it like this. So we sum up now over all vertices, and we multiply by the entries of the adjacency matrix. So it's not, so we don't need to specify whether our vertex VL is a neighbor of Vj or not, because those that are neighbors are going to be counted, right? Because there will be 1, and those that are not neighbors, they will just add zeros, so it's not going to change anything. So that's a shorter way to write it. Now, okay, so this is a summation, so let me write it maybe more, kind of expand this. So basically what is happening here? So we have, okay, so for the first vertex, we will get I1, the entry of a to the k, times the, maybe I want to use a different color here, so times the, so this was L, Lj entry of A of the adjacency matrix, plus then we have a to the k, and we have the entry, no, this was, sorry, this was 1, this was that was correct, right? So the first entry, and what am I doing? So this is 1, the first vertex, then we have the same thing for the second vertex. And again, I want to use the different color for A to J, and so on. Well, maybe let me write one more. A to the K, the I third entry, and we multiply it by the 3J entry of A, and so on. Then the last entry, last summoned here, is going to be the I-nth entry of a to the k multiplied by the n-jth entry of a. So, and here in red, we get the ith row of the matrix A to the kth power, right? Because I is fixed, and we take I1, I2, I3, and so on, In. So that's exactly the ith row of A to the k. And in purple, we get exactly the jth column of the matrix A itself. So we take the ith row of A to the k and we multiply it by the jth column of A. Multiply it exactly the way we did with the matrix multiplication. So what do we get? We get the product of the matrices A to the k and A, and we take the ijth entry of it. So, but A to the k times another A is just A to the k plus 1th power. So we get exactly the ijth entry of a to the k plus 1. So we started from the number of walks from of length k plus 1 from vi to vj, and according to this computation we get exactly the ijth entry of the matrix a to the k plus 1. So that concludes the proof. So all right, so that's it. So let's last thing to do is to consider an example. So we still have the same graph in this example. So we already computed the adjacency matrix. Moreover, we already computed the square of the adjacency matrix. So let's also compute the cube here. So for the cube, we need to take the a squared. This is the a squared, and multiply it by a again. So let's do that. So we take the first row, multiply it by the first column. We get 2, right? Then we multiply it by the second column here. And we get 2 plus 1 plus 1, 4. We multiply it by the third column here. We get 2 plus 1 plus 0, 3. And for the last column here, we just get 1, right? So it's 0 plus 1 plus 0 plus 0. Now we do the same thing with the second row here. We get 0 plus 3 plus 1. So that's 4. And then by the second column, we get 1 plus 0 plus 1 plus 0. So it's 2. By the third, we get 1 plus 3 plus 0 plus 0. So that's 4. And then 0 plus 3 plus 0 plus 0, right? So that's a 3. Okay, let's take the third row here. So we got 1 plus 2, 3. Let me not say zeros. So and here we got 1 plus 2 plus 1. So that's 4. And for the last 1 plus 2 plus 1, 4. For the third column, we get 1 plus 1, 2. And for the last column, we get just 1. And finally, the last row here. So we got 1, right? So 0 plus 0 plus 1 plus 0. Then we got 3. Then we got 1 again. And finally, we just get 0. Right? Yes, 0. All right. Well, let's check something. So let's pick some entry here, maybe this one. So this is the first row and third column. So that should correspond to the first vertex and the third vertex. And we are looking at walks of length 3. Walks of length 3, so from V1 to V3. So let's try to find all of them. So one thing we can do, we can just use this edge V1, V3. So what we'll do, we'll go along it, then go back, and then go back again to V3. So that's like this. So that's a walk of length 3, right? So we got the first one is going to be V1, V3, then back to V1, then back to V3. So that's a walk. Not a path though, but a walk. Okay, so what can we also do? Maybe let me use a different color. Say this one. So we can also start from V1. So I claim that we actually have to go to okay, we can start from V1, we can go to V3, all right, but then we will go to V2 instead, and then go back to V3. So that is what? V1, V3, V2, V3. So that's another walk. And finally, we can also do, okay, so which color? purple. I already used purple, right? Okay, anyways, blue, red. Okay, so we can also go, finally we can go to V2, come back, and then go to V3. So that is V1, V2, V1, V3. So all these walks are kind of silly, right? So we repeat, we kind of go back and forth a lot, but that's because V1 and V3 are actually connected by an H, so all the walks of length 3 between them are kind of silly. So, but that's all. There are no other walks of length 3. So maybe let me clear that, because I don't want to, I will want to use this again. Another interesting thing that this matrix tells us now is that there are no walks of length 3 between from V4 to itself. So if we stand at V4 over here, there is no way to get back in 3 steps. Well, for the first step, we would have to go to V2, and then, well, we can come back in 1 step, but that's just 2 steps, walk of length 2. And there is no way to get from V2 to back to V4 in exactly 2 steps. So that's why we get 0 over there. Well, that's the final thing. For our final thing, let's also compute the 4th power here. So for the 4th power, so one reason I want to do that is that for the 4th power we actually didn't need to compute the 3rd power. We can take the 2nd power and multiply it by itself. As we do that, we will get the 4th power. So we could have skipped the computation of a cubed. But anyways, let's continue. Let's compute a to the 4th power. So first column by first column is going to be 4 plus 1 plus 1 plus 1. So that's a 7. Second column here is 2 plus 5 plus 1. 2 plus 5 plus 1 is 8. And then third column here, 2 plus 1 plus 2 plus 1. So that's a 6. And the last one here is 2 plus 1 plus 1, 4. Then the second column here, second row here. So 2 plus 3 plus 1, 6. Something is off. 2 plus 3 plus 1. Right, so this should also, I made a mistake before. So so here we were supposed to multiply the first row by the second column. So that is a 2 plus 3 plus 1. So that's a 6. Okay. And now the second row by the second column. So that's 1 plus 9 plus 1. So that's 11. Then by the third column here, it's 1 plus 3 plus 2. 1 plus 3 plus 2, so that's a 6. And then 1 plus 1, that's a 2. Okay, third. 2 plus 1 plus 2 plus 1. So that's 6. By the second, it's 1 plus 3 plus 2. That's another 6. By third column, it's 1 plus 1 plus 4 plus 1. 1 plus 1 plus 4 plus 1. So that's a 7. And by the last one, it's a 3, right? So 1 plus 1 plus 1. Okay, and finally, the last row here. So we got 2 plus 1 plus 1, so that's a 4. Then we got 1 plus 1, 2. And then finally we get 1 plus 2 plus 1, so that's a 4. 1 plus 2 plus 1. So again, I made a mistake. Sorry. So this 3 should be what? Let's check. So we're doing here the third column, or third row, and we multiply it by the last column. No, that's correct, right? No, that's a 4, right? So it's a 1 plus 2 plus 1, 4. Okay, and finally, last row by last column is just 1 plus 1 plus 1, so that's a 3. So I think that should be good now. So that's our product. So maybe let's try to investigate one of the numbers. Maybe let's take this 6 here. So this is V2 and V3. So we have V2, we have V3. So there should be 6 walks of length 4. Okay, so what we can do, we can go from V2 to V3 through V1, right? So we can do V2, V1, V3. And after that, we can go backwards, use of one of the edges at V3 to go back and again. So we can do V2, V3, or we could have similarly done V1, V3 there. So that's 2. Now we could have done something silly in the very beginning at V2. So we could have kind of use the same 2 steps as here. But before doing that, do say V2, V1, V2. Or we could have done V2, V3, V2. Or finally, we could have done V2, V4, V2. So there are 3 edges at V2, and we could have used any of those to do this kind of back and forth thing. So that's 5. There should be one more. Okay, should be one more. Let's try to find it. And I cannot find it right away. Yeah. We can go from V2. We can go from V2 to V3 right away, but then do the circle. So we can V1, V2, V3. I think that's another one, right? So if we would do the circle opposite way, then we would get something that we already counted. But this way, it's actually new. All right. So I think that's it. That's the 6 possibilities. But you can see that it's not that obvious to find all the 6 possibilities, and the matrix actually counted for us for free. So that's it for today. Thank you very much.